In this video lecture, we're going to cover Chapter 17, Section 6, and we're going to look at Q versus KSP and see how we can determine if a precipitate will form. A couple things to remember. Anytime we're talking about a KSP reaction, you always have your ionic compound solid in equilibrium dissolving into the aqueous ions. So we have to remember that. And for this case, I'm using just AB as an example. That would be some type of an insoluble ionic compound. I know KSP would be A times B, B minus, excuse me. Let's fix that. Right, if A is a cation, B is an anion. And you would solve for K if you had equilibrium values. So what we're going to look at here is QSP, or just Q. I'll call it QSP to be specific, where we have A times B, but here we do not know if we're at equilibrium. And remember that KSP talks about when you multiply these together, that gives you the definition of a saturated solution. So the solution is holding as many of these aqueous ions as possible. So if you have a saturated solution and you added more AB, it wouldn't dissolve, it would precipitate out on the bottom of the beaker. So let's go over these points. In a solution, if Q equals KSP, the system is at equilibrium and the solution is saturated. Again, so if it was a saturated solution, you would see it would just look like water, or you would see no solid at all. If Q is less than KSP, more solid can dissolve until Q equals K. So if Q is less, that means when you multiply these together, it's a smaller number than K. Therefore, you could add more of AB to your beaker and it would dissolve. Lastly, if Q is greater than KSP, the salt will precipitate until Q equals KSP. So if Q is greater, that means that there are more ions in solution than are stable. So what would happen is if you added a seed crystal or did something to disturb the equilibrium, you would see a solid form. And in this beaker, what we're looking at, we have the clear, colorless silver nitrate, adding potassium chromate, and we've added enough, so we're forming the red silver chromate. So we're looking at this double displacement reaction. So another example here, so the same photo we were just looking at, and now what we're looking at is a supersaturated solution. So the reason you would know it was supersaturated is if you calculated QSP and it was greater than KSP. You add a seed crystal to disturb the equilibrium, and then you see all of the excess solid forming. In this case, this is sodium acetate. And this YouTube link, I want you to go there. There's a link on our Canvas page, and you can watch this form. So a supersaturated solution will precipitate if a seed crystal is added, and that's what we're observing there. Now let's look at practice exercise 11. So it says, will a precipitate form when 0.050 liters of 2 times 10 to the negative second molar sodium fluoride is mixed with 0.01 liters of 1 times 10 to the negative second molar calcium nitrate. So the first thing we need to figure out is what is the possible precipitate that will form. So let's write our double displacement reaction. Sodium fluoride, aqueous, because sodium is always soluble and you're given a molarity, therefore you know it's aqueous, plus calcium nitrate. And the reaction, so this is just a double displacement reaction from Chem 60, Chem 101. We're going to form sodium nitrate. And I know that's aqueous because sodium and nitrate are both always soluble based on our solubility rules, plus calcium fluoride. And this is the one that might form a solid if we have a high enough molarity of the calcium ions. And then for good measure, we can balance it. So I've got 2 nitrates on the left, so I need 2 over here, 2 fluorides. Okay, I think that looks good. So the problem that we're interested in is determining if calcium fluoride solid will form at these concentrations. So I know my KSP is going to help. CaF2 solid, my KSP reaction, the ionic compound forming ions. So KSP where these are both equilibrium values, and we can look up the KSP value from a table. And in our textbook, we have the KSP as 1.46 times 10 to the negative 10th. So we get a really small number because there aren't many of these ions dissolved in solution because calcium fluoride in general is not soluble. However, we have very low molarities, so we're not sure if we're going to form a solid or not. So to do that, we have to solve for QSP. So QSP is just our calcium that we have in this beaker times our fluoride that we have in this beaker. In order to solve this problem, we need to find our new molarity. So what's happening? I have one beaker, and in that beaker, I'm adding my sodium fluoride. So for the sodium fluoride, I have 50 mils, or 0.050 liters, of 2 times 10 to the negative second molar NaF. And I'm adding to that calcium nitrate. And I'm adding 10 mils, or 0.010 liters, of 1 times 10 to the negative second molar CaNO3 So we're essentially diluting both of those because we're combining a new total volume. So let's figure out how many moles I have. So when I multiply 0.010 times 1 times 10 to the second, I get 1.0 times 10 to the negative fourth moles of calcium nitrate. And the ion I'm interested in is calcium. And I know for every 1 mole of calcium nitrate, I've got 1 mole of calcium. So that I can do that 1-to-1 mole ratio in my head. I now divide by my new total volume to get my molarity. And I know my new total volume is that 0.010 plus 0.050 or 0.060 liters. So the molarity of the calcium, 0.0167 molar. And now we're going to look at the sodium fluoride. And again, the ion I'm interested in is fluoride, right, because of that and this. And I just found something that I missed. So hopefully you caught this. Coefficient of 2, and I always make this mistake, but normally you guys are there with me in class to tell me I forgot it. I hang out with the acid-base reactions so much where we have the 1-to-1 mole ratios. It's really easy to forget the exponents here. So use this as a reminder. Don't forget your exponents. So it's squared because of our coefficient of 2. So that's why I'm interested in fluoride. So let's find our new molarity of the fluoride. And I have 0.050 liters times 2 times 10 to the negative second molarity, which gives me, so I'm multiplying those together, 0.001 mole of NaF, 1-to-1 mole ratio with fluoride, which is what I'm interested in, divided by my new total volume to get my new molarity. And I end up with 0.0167 molar fluoride. And I forgot a 0 here. Hopefully you caught that also. 0.00167 molarity calcium. Okay, so now what I have my calcium molarity to plug in for here. I have my fluoride molarity to plug in here. So now I can solve for Q. So QSP equals my calcium, 0.00167, times fluoride, 0.0167 squared. When I multiply these together, I end up with 4.9 times 10 to the negative 7th. So that's my Q value, and now I have to compare it to K. So K, SP, from the text, 1.46 times 10 to the negative 11th. So I can see right away that Q is greater than K. That means the solution is supersaturated and precipitation will occur.